Hello, everyone. Welcome to our group presentation. We are Group 10, Fall 2021, supervised by Dr. Moustafa Youssef and Dr. Hossam Sharara. We will start our presentation by going through the bullet points that we'll be talking about today. First off, the problem definition. We'll define our problem, and then we'll speak about our two models. And finally, we'll speak about the reinforcement outcome that we have achieved throughout the 2 semesters. First off, with the problem definition, you all know about localization systems like GBS, for example. It's a very well-known localization system worldwide. However, GBS is an outdoor localization system, meaning it does location tracking in outdoor environments and outside buildings. There are other type of localization called indoor localization used in office environments and inside the buildings. And just like GBS has many applications like traffic tracking, indoor environment also has very promising applications. For example, like navigation inside business-driven entities like malls and governmental entities like airports and so on. And it can enable many targeted ads, which will increase the revenues of companies using these services. There have been, of course, other attempts in creating indoor localization systems that tackles this indoor problem. However, there is a gap in the literature because there is not one universal system like GBS, for example, in outdoor that can work in an indoor environment that it has never seen before. And hence, the scope of our work was to build an indoor positioning system that work in cross-building settings, and it can do proper localization on buildings it has never been trained on. In the literature, there are 2 types of localization systems. First, ones that use dedicated structures like LiDAR sensors and so on that was built specifically for localization. These usually have very high accuracy, however, because they are built for localization. However, they have very high costs sometimes, and they are hard to install. Other type of literature uses already existing infrastructure like Wi-Fi networks. However, these were not essentially built for localization, and hence they give very poor accuracy. However, they are very ubiquitous. And hence, we are trying to work on this ubiquitous system to enhance their accuracy in cross-building and maintain this accuracy in cross-building. And hence, we have identified that this is a problem that has many dimensions. First off, we will be working with already existing infrastructure like Wi-Fi, and changes in the Wi-Fi infrastructure to maximize or enhance communication might affect the localization. There's also the environmental variables, for example, like the floor planes that is different between different buildings, different walls existing in different places. And there's also the problem of changing furniture and the people density changes throughout the day. Maybe at the morning it's much crowdier. Finally, for the building characteristic itself, for example, the material that the building itself was built on and so on, and the location of the building, is there any signal density that does a very large interference in some buildings compared to others? So we have come up with 2 models. The first one deals with the problem of the Wi-Fi infrastructure. It's called cross configuration. The second model was called cross localization, which deals with the problem of the environment. And we'll start by speaking about the cross configuration with my friend Ali.
So our first attempt to solve the problem of cross-building localization was introducing the cross-conf system. But before diving into the details of our system, let's define what is a configuration. A configuration is defined as the distribution of the location of access point in the space. So any addition or removal or a change of the type of access point can constitute a change to the configuration of our system. So here is our system architecture. We have 2 phases, the online mode and the offline mode. The offline mode is about training our models to be able to operate in the online mode. For the offline mode, we have many modules like the AB location collector, access point location collector, the signature collector, the preprocessor module, the data augmentation module, and the model trainer. And for the online mode, we used many of those modules before, and we added the location prediction module, which uses and utilizes a deep learning model. For the preprocessing module, previous systems takes all the access point information into account, but we try to come up with generalizable features throughout this preprocessing module. So we have taken all the RSS signals and we combined them with the X and Y position of each access point, and we sorted them descendingly depending on the strength of the access point. And we have taken the first K access points. And as you can see down the road in the result section, this K was determined to be 4. And we have performed the normal cleaning, like dropping of duplicate rows and changing null values into -100 dp. And this diagram shows how the signals was used before and our transformation over it. Performing such a transformation in the pre-processing module makes us focus on a virtual building, meaning that instead of focusing on the entire building, we are focusing on a smaller area, and by focusing on such a smaller area, we can reduce the margin of our error. So our model architecture is that we are taking those features, taking those signals and position of access points as features into a model. And for this model, we are using a simple feed-forward neural network, which is comprised of hierarchical structure. And the output is a regression output constituting the X and Y in the environment. And we envision 2 data augmentation techniques inspired by previous work in the system, on the field, like the drawing of random access points and the drawing of strongest access point. For the drawing of random access point, we try to simulate the drawing of access point in the physical real environment. So we are randomly drawing different number of access points, like 1 or 2 or in the number of access points. And for the drawing of strongest access points, we tried to make sure that our model is not overfitting the position of the strongest access point as the position of our user. So we try to drop the strongest access point in and train our system to do proper localization using this improved data. And for the data collection section, and Abdelazim.
So for data collection, as you have seen, our data set relied on 3 buildings at AUC, mainly the library, the CSE department, as well as SSE at large. As you can see from the data collection details in the table in front of you, there is the range of the points that we collected ranged from 4,400 points all the way to 6,600 points. The number of access points ranged from 6 to 11. The areas were a variety as well as the density of access points. However, we try to keep the collection spacing constant, as it is one of the variables under our control. As you can see, this is our application which we used to collect our data. It has the basic features of collecting samples and predicting the locations of access points. We have also introduced a new feature, which is working with during the online phase to localize and position the user, which we call the online positioning feature. And now for the cross-conf results with Omar Shaheen.
Okay, now the results. So I will start with drawing access points. So an access point won't be available for use in indoor localization system if it just malfunctions or were removed. And this experiment was designed to test the robustness of our system against dropping different number of access points. So the experiment starts with 11 access points configuration, the one you can see here. And we drop from 1 to 5 access points and test the performance of different models on the test data. So in the first configuration, you can see here, we dropped the access point in yellow and left 10 access points. In the second configuration, we dropped 2 access points and left 9. In the third configuration, we dropped 8, and so on. We test the performance of different models on the test data, and here's the results. This is the error of different systems in meter. As you can see, our model cross-conf is not as good as the other systems in the first configuration, but the error does not rise significantly as we drop different number of access points. On the other hand, the error of the other systems increases, giving our own model the lead after dropping only 2 access points. Now the changing access points location. An access point location can change, causing a disturbance for the indoor localization system. So you will need to retrain your model or come up with a totally new model. So this experiment was designed to test the performance or the robustness of cross-conf against changing the location of access points. This experiment starts with 6 access points, as you can see in this configuration, and we drop from 1 to 5. We change from 1 to 5 access points and test the performance of different models. The first configuration you can see on the right, we changed the location of 1 access point. The second configuration, we changed the location of 2, and so on. Here's the results in meters. As you can see, our model cross-conf far surpasses all other models, since it takes the strongest 4 access points, and it also takes the consideration, takes into account the location of the access points as an input. Here's the evaluation or the impact of trained data reduction. Here we test the robustness of our model in case we have fewer number of data points. And as you can see, the error does not rise significantly if we reduce the data used by 10 or 20 or 30% or even 40%, but it rises significantly from 60 to 70, but that's an extreme case. But it shows how robust our model performs in case our data, our training data was reduced. Now I will leave you with Amr.
So after you have seen the performance when we reduce the number of access points we used for training, you will see the effect of different data augmentation techniques. As you can see, this is in this graph, it shows us how the vanilla performs and the error of the vanilla without using any data augmentation techniques. We have also introduced random dropping of access points and dropping the strongest access point. We have also tried to mix both techniques. And as you have seen, the random dropping and the dropping of the strongest access point result in an improvement of around 20%. However, using both is only 25% better, which shows us a marginal improvement without a huge increase. We have also decided to work around with a dropout rate in our model. When we drop out up to 30%, we have found 30% to be the sweet spot where we do not risk any decrease in the localization error. It actually dramatically decreases around 30 points without increasing any weight in the model. We have also worked with the select and decay value, which is the number of access points. As you have seen, the number, when we use 4 access points, it results in roughly one of the best errors without increasing the complexity, which leaves us with the end result for cross-configuration, which is that we have finally tackled the problem of the Wi-Fi infrastructure setup. However, it remains to tackle the problems of environment and building characteristics. And now I leave you with cross-lock to tackle the second problem with my colleague, Mohamed Hemdan.
Okay. So our approach here is to build a global model for all buildings, so that given a set of buildings that our model is trained on, our model can now generalize to other models that he has never seen before, and even give better results on these. So in our experiments, we trained our model on the library and the CS department and tested on the SSE corridor as our unseen building. So our first approach was to use the cross-conf model, since our cross-conf model uses a standardized and generalizable input vector. So we use both this input vector and the cross-conf model in our cross-building case. In order to compare our system and examine the performance of our system, we compare it with standard solutions like the averaging and the weighted averaging of the access point locations. And as you can see here, our model gives the best results on both the unseen and the seen buildings. However, there is some gap between the performance of our system on the seen buildings and the unseen buildings, and that's what we are trying to solve in the second approach. And the second approach is basically we are trying to incorporating images, since the RSS distribution inside the building is highly dependent on the floor plan. So we are trying to fit the floor plan alongside the RSS and locations of the access points to be fed to our model. However, before fitting the floor plan image to our model, we did some pre-processing. The first is marking the walls as ones and everything else as zeros, since walls are the most significant contributor to the RSS disturbance. Second, and since the strongest, our location is high probability to be in around the strongest access point, we crop the image and take a snippet of n by n meters around the strongest access point, as you can see here, to be fit to our model. And since we have a limited number of these snippets, we use the pre-trained model, specifically VGG network, to extract features that are relevant to our neural network. We use some transfer learning to extract somehow relevant to our application. We then concatenate this with the RSS and locations of the access points to be fit to our neural network and output the location. We use two techniques to output the location of the user. The first one is the regression, and the second one is called the classification. The classification gives better results than the regression, and as we increase the number of grid cells, the accuracy increases and the location error decreases until it reaches 3.5 and 3.47 meters at the end. So at the end, we can see that our cross-lock model gives the best results both on the seen and unseen buildings. And it gives a middle ground between the performance of the cross-conf model on the seen and unseen buildings. So we can see that our model is now robust against the changes in the Wi-Fi infrastructure and also robust against the changes in the environment. Now I'll leave you with the reinforcement outcomes.
Okay. It seems like it was a long journey that we took, me and my friends, to reach these reinforcement outcomes. It was a journey of failure and success, trying out again until we reached the desired reinforcement outcomes. So as a first outcome, we achieved a research. We successfully completed our paper about cross-configuration work. It's now completed. Not only this, but we're considering it to be submitted to ACM 6 Spatial, which is a really good conference to localization systems. Now to the industry, which is our second outcome. We already implemented an online app tracking, which serves as a proof of concept. Not only this, we also will work after we finish this semester on our goals towards the industrial outcomes. So when we say industry, we're talking about unique selling points about our application. We're betting that our application, in the first place, it's easy for deployment, just train once, localize it wherever. Second thing, adaptability. Our application adapts to the new changes in the Wi-Fi infrastructure. Moreover, it's so affordable where we will offer a lot of wide variety of paid options as well as a free option with ads. So for the monetization models, we implemented two models, freemium and subscriptions. Freemium will be more to the community. It will include ads and it will localize it only. But for the Primlock, it will be ads free, and it will allow the users to use the navigation and location determination, both of them. For the subscriptions, it will be mainly targeting the enterprise. It will be for businesses and institutions to locate them in malls, for example. It will be used for marketing reasons, for the warehouse monitoring, and for university and hospitals. We also did some collaborations with the Philograph design students. I hope you like these designs. These are the app, and that's it. Thank you.